Hello. I think I will switch to English in case somebody jumps through who doesn't speak German. I'm not Michael Falkenthal, as you may have expected here. I'm Matthias Kaiser, his colleague. He's currently busy, so I'm taking over. But we will also have a nice talk. I also know it's very late in the day, so I hope it will be still fine and you can follow me. It's not too technical. We will talk a little bit about how quantum applications or quantum software can be implemented and also deployed easily and fast. And we will also talk a little bit about some pitfalls of current quantum development. So when we talk about quantum development, I mean in quantum and computing in general, there are a lot of different problems. But of course, quantum software development has also many problems. I myself, I am a physicist. I have studied physics, and I can program. However, that unfortunately doesn't make me a programmer, because to be a programmer, you have to worry not just about making some kind of code sometimes work, kind of. You have to actually make very good code that works all the time, that is efficient and is robust. And the problem is that most of the quantum software developers nowadays are physicists and mathematicians. I know myself what kind of code we write. It's not up to standard when it comes to real development work. That is one of the problems. Then on the other side, when there is quantum code developed, it's often in code snippets and lying around somewhere on laptops, in Jupyter notebooks, on GitHub, wherever it is, and it's just code snippet that is once written, once used, and then forgotten about in many cases. Also a good point is that many people often forget is that a quantum algorithm doesn't make a quantum solution. It's just an algorithm. The solution has to be built around that. And that also often means, or always means, that it's a hybrid solution. So everybody's talking about hybrid algorithms, full quantum algorithms. Any quantum algorithms will always be hybrid, because as soon as you start to do data preparation, you do some management of users, some different kind of things around the actual algorithms, is already not fully quantum anymore. It is, in fact, already hybrid algorithms. And then you have the problem that you have all of these different kind of things that you could use to write your quantum code, to deploy your quantum code, and it's a huge mess and nobody really can navigate it, especially not people in big companies, which have usually the developers there a more classical background and have then to deal with some code they don't really understand and don't know what really to do with it. So this is the biggest problem in the end, that you have quantum developers and you have potential users, and it's not really clear how they efficiently and well can work together. This was actually the problem we came also to at the Planck project. Who doesn't know the Planck project? I think now I'm back. Okay, I don't know what this was. It's a project financed by the German Ministry of Economics that had the task to try, or has the task still until the end of the year, to try different applications of quantum computers in the industry. And we had exactly that problem, that this connection between the industrial users and the quantum developers was not really clear how they could work efficiently together, so that the industrial users can use quantum code in a way that they already know and it's easy for them to do. But the quantum developers also don't have to learn all of the skills around. They want to concentrate on their quantum algorithms. And what we did is we developed the Planck platform, which is exactly doing that. So that allows the quantum developers to develop quantum code, for example in Qiskit or whatever else, then upload it on the platform. In the platform, it's then put into a Docker container and offered for the user as a usable service. So the user only has to deal with the REST API service, what industrial users are already used to do with classical code as well. So they don't have to change anything. In fact, they can actually replace classical optimization parts of their existing software with a quantum system. At the moment, just for a POC, because we all know the quantum hardware is not ready, but that also makes the entry level for industrial users for POCs much easier than when they have to reinvent a whole application around that. And in the end, the goal of this all will be that we also will allow the quantum developers to monetize their code. So that means they would put their code on the platform, would put a price tag on, the industrial users could consume it, pay as you go. Then, of course, the quantum developers would receive that money and could that way monetize their code without having to worry about all of the infrastructure which is around. We also offer connection to quantum hardware. Here you see a couple of examples. We have also just announced the cooperation with Sequence. Our CTO did it yesterday. So we're really pushing also this idea of a European quantum cloud forward. So what does the platform do? First of all, it offers tools and infrastructure to the quantum developers to develop their code. We have also, for example, development patterns which help the development of quantum code. We have example implementations, use cases on the platform. But on the other hand, it also allows the industrial user to learn more about quantum computing, to find use case examples which fit maybe with their own problems that they already have, so they can match that up and find possible solutions for the problem they have or for the problem they want to solve with quantum. And of course, in the end, also the quantum services. Within Planck, we by now more than 100 companies that are organized within the Planck consortium. You see here a couple of names. The community is still growing. It will also exist after the funding is over, end of the year. We are currently discussing in what form also the community of different industrial players will go on being a community. And with these over 100 different players, we have tested more than 30 different use cases on the platform. So that means we know very well how to implement POCs in this case, of course, proof of concepts, and work in a way that as well the quantum developers are happy, but also the industrial users get what they know and want. How that in practice would look like is like this. You have that's actually the most important thing is actually the service orchestration, because as I said before, a quantum solution is not a quantum algorithm. So somehow when you have a quantum algorithm, you have to build a quantum solution out of that, and that you do through service orchestration. What we mean by that, you have different kind of quantum services, also maybe classical services that you have to put together to build one solution. So we are making now this example of, I know it's not from the quantum computing side a very applicable problem, traveling salesperson, so delivery truck optimization. But it's a good example because it's very easy to understand how that works. So you have you have a universal service, so you have some kind of quantum annealing service that sends something on a quantum annealer and gets some result back, whatever that may be. And you have an implementation of a traveling salesperson problem that you want to then send on this quantum annealer. So in fact, to solve your problem, you don't just need the quantum annealer algorithm to send it to the quantum annealer and get a result, but you also need the implementation of the traveling salesperson problem. And both of that is then going into the solution, finding the best route for a parcel service, for example. So you see already it's not a single algorithm that works here, but here already we see that it's several. There's actually a real implementation we did on the Planck platform, so we know what is necessary to make that work. Fleet route planning, maybe to explain it for you to more in detail, probably you all heard it, so I will be short here. You have some kind of dispatcher that is here. You have a ton of different parcels, or to make it a quantum problem, it's not a ton, it's just a couple of. And you have a ton of different couriers. Also on a quantum computer, it's just a handful, maybe. For real application, of course, not yet working, but as an example, it works. So you get this kind of graph out of this, where you can see the distances between the different points where you have to put the different packages. Now you want to optimize that. That means you want to distribute the packages on the trucks in the best way, but then also send the trucks in the best possible way to use less fuel, be faster, be more efficient with your time and money. So what you do, what we would do in this example, you see here how we would orchestrate that with different kind of applications. The hammer indicates it's a classical approach. The atom indicates it's a quantum. So you see that actually in the solution of the problem, most steps are completely classical. There's just one process, is the solving of the TSP, which is actually quantum, which is basically done on a quantum annealer. What we did is we transformed the input data. So we had some input data that was, of course, not in a way that it was understandable for a quantum computer. Then we clustered the graph, so we cut it in different kind of subclusters, and then we run the TSP. Reason being that this is a too big problem for a quantum computer to solve. So we clustered it, then we solved the TSP for each of these subgraphs, and then transformed the result in something that makes sense for anybody who reads that. So this is basically how, like, very, very basic workflow of such a quantum service would look like. And how that then in the end would look like, because that is still not a solution to the problem, because a solution to the problem requires maybe access to a database where all of the streets, where all of the couriers, things like this are. Then there's maybe a graphical user interface that actually then tells the driver where they have to go. So this workflow can then be embedded somehow into a existing application. Exactly. The problem there is, of course, that when you want to do that, there's different kind of problems. For example, are the two platforms where this is running on are compatible? Are they written in the same programming language, both of these solutions? And if they're not, how you resolve that? And many, many other problems that may arise from putting these two things together. So the elegant solution of this is, of course, as maybe there are some programmers here, is by basically making services and connecting it over API. And this is exactly what we did. You can do it as it is currently. That is basically you have the clustering part, which I talked before about. You have the TSP solver, and both have an API, and you connect it to the legacy process that the customer already have, and boom, you have your solution. The even more elegant way is, of course, to bind that together, make an API on both of them, and then offer it to the cluster. And the even better one is that you push some of the business logic already in this application, because then you have a real business application that actually solves a problem for the user. And this is basically what we're currently working on Planck. Here we are. And this is what we're currently implementing, so that you can make bigger and better and more usable quantum applications that have actual real value applications, or at least at the moment for easy way to do POCs. How to monetize the code. So when you're a quantum developer and you want to monetize code, there's a lot of different problems. It's not just writing the code. You have to worry about the technical interfaces, APIs, how you want to connect it to anything, service level agreements. So if you want to make money out of that, somehow you have to agree with your customers on what are the terms of that. You have lifecycle management. You have to have some kind of payment system connected to your thing. And this is basically what we take over at Planck, so that the quantum software developers can actually concentrate on doing the algorithms and the quantum code, and we do all of the infrastructure around that helps to bring it to the customer. That's actually exactly that slide. So we have the what Planck is of course I explained currently the marketplace where industrial users could purchase these access to these services. But we also have a collaboration platform, for example, where different partners collaborate. That comes of course out of the Planck project, which it was until now and will be until end of the year. But this will also further go on. Connected to that is, of course, also knowledge platform. So a big part of that is also collecting use cases, collecting different algorithms, and basically educating the potential users of that, because it's often also a matter of information that is required to get the first steps into quantum. Then the serverless quantum platform, connection to quantum hardware, whatever it may be, benefit for the industrial user. They don't have to log in to one specific hardware. They can test out different hardware, different algorithms, and don't have to worry about that they maybe have bet on the wrong horse too early, because we all know it will not stay the next 10 years with 15 different implementation of what is a qubit, but it will likely converge to one or maybe two different implementations. So if you have bet too early on the wrong one, that might be a problem for you, or at least a risk for the company in such a project. Knowledge platform I talked already about, and then of course what I talked before about is the quantum orchestration platform that helps you to orchestrate the different services and make actually usable applications out of that. Yeah, that basically just shows what I just said. In the end, we want to get away from code snippets that can be used only once to actually scalable quantum solutions that can be reused and also made better, improved, and then reused, and then always connected to the same way. That allows also industrial users to always use the newest thing, because if a quantum service is improved and still on the platform, they can still over the same way connect to that and always have the newest implementation of that algorithm, implementation on the new quantum computer. So that means we also have that that layer of continuity for the industrial user. They don't always have to worry about, okay, IBM has just brought out a new quantum computer. What I do now with my quantum code that is useless. This would be the solution for that as well. Here it is. It's already existing. You can check it out here if you scan this QR code. You can also walk around. We have a small booth there. You can check it out. You can also apply for a login. Currently, you still have to go through a small authentication process, because we're financed by the BMWK. They have some controls on that. But you can check it out. You can definitely check out all of the information. There are also already code snippets on it, which you can use for starting your own project by just checking out what others did. You can read about use cases and many other information you will find there. So even if you don't want to use it for using our services, it's a great platform for just getting information. I heard already that many of the developers use our development patterns that are freely available on the platform, so just check it out if you like to. That's it. If you have questions, please feel free, but you can also catch me over there in a moment if you like to. Thanks.